The process was basically started off by Steinmetz, and then there were two other allied scientists, Bloom, and I forget the name of the other guy, Boyajian. Bloom was the first one to discover that the dimensionality of magnetic inductance should be, rather than L squared, L being length, should be 1 over L cubed. In other words, per centimeters cubed. But never went anywhere with it. And then Bewley, which was the one that really developed all the differential equations for describing this stuff, kind of forgot about mutual inductance in its proper dimensions. And even though quantified all of these things very admirably in his book called Traveling Waves on Transmission Systems, probably one of the best books on electric waves ever written, he still failed to understand the true nature of the longitudinal wave and the dimensionality of mutual inductance. Now, of course, in the double energy flows, when these things combine, we have the longitudinal wave, the wave of Tesla, and we have the transverse electromagnetic wave, the wave of Hertz. This is the wave we use today for transmission. This wave has become completely forgotten, unless it incidentally appears because you have too big of a loading coil. Oh, piece of paper there. Okay, I think that's it for the diagrams. Yep, that's the last sheet. Okay, that kind of wraps up what my talk is on this. I know it's a pretty shotgun approach and scatter, but I tried to run you through the whole arrangement here. I think any experimenter knows where to begin. You're going to end up with an SWR of infinity as your desire rather than 1. You're going to find out that the plate current will dip down real nice. Your tank circuit Q, irregardless of what the ham radio book says, should be at least 10 to 20,000. The way to accomplish this is with extremely heavy sheet copper windings and large quantities of vacuum capacitors in parallel. You'll end up with circulating currents of hundreds, if not thousands, of amps. The other approach is to use large series resonant circuits or resonant coils. You'll end up with voltages of anywhere between 50,000 volts to 1,000,000 volts. You will learn all about electrostatic gradients, punch through, flame outs, and all the pitfalls. It will be very difficult. And you will learn about ground impedance and the undesirability of inductance. A straight wire is no better inductance. There's no better way to establish an impedance than to have a nice long piece of number 8 gauge wire going from your rig to ground. You might as well put a resistor in the circuit. Everything has to be done with sheet copper. Any effective conductor of radio frequency current has to be 1/3 wide as it is long. It can't be any thinner. Ground impedance has to be at least 100th to 1,000th of an ohm. If you can deal with all these things, you can get rid of your antenna and you'll have no more complaints from your neighbor except for that did-it-ah-dah did-it coming out of their telephone. So I'm going to turn this over to Chris, and he's going to go through some ancillary. Oh, actually, I was going to give you one more demonstration here. I'm sorry. We have the two networks. We have the longitudinal and transverse networks.
Hold them up, Eric, and show it to them.
Well, it's kind of hard. But we have, as you see, the network MK and network LC, which is shown as 2 and 4 on there. These are laddered up in what are called an artificial transmission line, consisting of a long series of little capacitors and little coils. The transverse electromagnetic line here is 1,500 meters long, electrically. Now, if we hunt for its resonant frequency as a quarter wave transmission line, in other words, creating an impedance at one end and an admittance at the other end, or closed and open circuit. And we'll use the AC voltmeter here. You notice we only have to use one wire. That's the key to Tesla. He developed the true monopolar electricity. Okay, we'll hunt for a resonant frequency. Okay, we get a little kick there, a little higher than before. I'm not used to this oscillator, so I don't know what its calibration is. It seems a little different than the original. Things don't always work out on stage as you would like. Okay, it was supposed to be 53 kilocycles, so this is showing it about 60. Okay, that is network number 4 up there, where all of the inductances are in series and all of the capacitances are in parallel. This is the transverse electromagnetic wave. By the way, the characteristic impedance of these artificial lines is 2,000 ohms. If we terminated the end in 2,000 ohms, of course, we would have SWR of 1 and no resonance. But I chose to leave them open and close at the other end so we'd have the resonance and be able to see the resonant frequencies. Okay, now on the longitudinal, we hunt for the resonant frequency. And here it shows up as about 100 kc. So we can see that in the longitudinal, the wave is propagating much faster than it is in the transverse. This oscillator is off frequency. It worked out that this one was 52 and this one was 83. And it worked out to be approximately that the ratio of the longitudinal transmission to the transverse transmission was exactly as Tesla stated, pi over 2. Now in the longitudinal, okay, we're used to dealing with transverse in a quantity which we call 1 over c squared. Somebody just brought up that recently. The c being a basic ratio between the magnetic units and the electrostatic units of the electrical constants. And it gives us basically a propagation through space as a length over a certain period of time. In the longitudinal, we're not propagating through space. We're propagating through counter space. Counter space is a situation where rather than expressing the length in meters, we have to express it in per meters. A completely inverse form of propagation. As an example, if we take an electromagnetic inductance coil, we find the inductance is proportional to the length of the wire, approximately, and the area enclosed by it. It's the quantity of meters that expresses the inductance. If we take a capacitor, we find the closer we bring the plates together, and the more we fill in the area, we're dealing with a situation that's in per meters. The electrostatic, as a natural propagator of longitudinal waves, always goes towards closeness. The magnetism always acts as a distance. So here is our basic difference between longitudinal and transverse. In the transverse wave, we're attempting to overcome distance by forcing our way through it. In the longitudinal wave, the 2 points are already there. Why fight it? They're already one. And this was Tesla's fundamental discovery. This is the way that he was able to light up a light bulb at his receiver. No RF amplifiers. They didn't have any of that back then. There was no transistors, no tubes. There was no Radio Shack. There was no Newark catalog. There was no Henry. There was no ohm. There was nothing. All there was brass and wood. And that was it. There was nothing else. And this guy, Tesla, was capable of transmitting electrical power over incredible distances with just simple, practical materials. There was no silicon, there was no nothing to work with. They just started to develop vacuum tubes. His vacuum tubes were all just like the light bulb. They were all just one-terminal devices. And they would produce incredible quantities of light in the same fashion as the sun, completely unlike the incandescent light bulbs of today. And all of Tesla's devices never used energy. Just like in a tank circuit, it was always returned on the opposite half cycle. So that concludes my talk. I'm going to turn you over to Chris for a few more demonstrations. Hopefully it wasn't too far out or confusing for you. I'm sure it was a lot of material. But also, I think I gave you something to start experimenting with. So those of you that love 160 meters, go to work.